Hi, everyone, and welcome to the Self-Sovereign Identity Workshop. This is a workshop to explain how self-sovereign identity works and why. And we're doing this internally at the Tonomy Foundation, and we'll be sharing this with the public as well. Oh, wait, I need to share my screen. Sorry, I'm going to start this again. Nobody can see my screen, eh? Let's go with this one. You can, this is not going full screen, is it? Ah, better?
Yes, this looks good.
Hi, everyone, and welcome to the Self-Sovereign Identity Workshop. In this workshop, we're going to be explaining how self-sovereign identity works and why this is important. We're doing this as an internal training for the Tonomy Foundation, but are planning on sharing this publicly. Very exciting. So what we're going to be doing today, I'm going to be giving you a bit of background. What is self-sovereign identity, how we got here. There's some ideology and architecture. I did have this is pre-work, but I'll just include it as post-work. Kind of the history of identity, how we got to self-sovereign identity, who's involved, how it works, getting into the nitty-gritty. This workshop's going to be focused mostly on that. It's going to get a little bit technical. And if you want something higher level, I've got some great links to follow up there. You can already find a lot of good high-level stuff. Finding the low-level stuff in a good format is the harder bit, so I focused on that. And then we're going to discuss some of the pros and cons and the challenges, and then why this is important. So just a little bit about myself. I am an experienced identity expert. I've been building, architecting, and leading teams in identity solutions for 3 years now, and been working in decentralized solutions for about 6 years now. So I am currently building the Tonomy ID self-sovereign identity application. I have led from start to finish the development of the MyD single sign-on solution, architecting the SSI Onto chain project with Gimli, as well as the SSI to NFC bridge. It's a hardware SSI solution. Part of this has been working with the EOSAO, now called Antelope community, and through that we developed the identity working group, the EOSAO DID method, and published the W3C verifiable condition standards, allowing multi-signature VCs and DIDCOM. And lastly, writing some privacy reports that are really relevant to understanding where this fits in, especially in a blockchain context. So, like I said, we're going to get into the meat of how it works more than the ideology. This is the really where I recommend you would start with SSI to get a broad picture of the ideology, the values, and the picture of why this is really important. It's very high level. It gives the 10 principles of SSI. It's also very fun if you're Dutch, which I know many of the people here are, because it gives a really good lesson on a big Dutch history mistake that happened during the war and why that was important. So we're going to look a little bit now at basically how identity currently works, or how it started. How it started was the old, well, the first thing I need to say here is that there's kind of two levels of identity in the internet. The first level is how our devices get their identity. That's called the Internet Protocol. And there's all kinds of identity at that level, DNS, SSL. And that's not really part of user identity, which is what I'm going to be talking about now. So that is a whole nother identity story. It's related and relevant, but I'm going to be talking about user identity. And how that started was people got a username and a password, and they would send that to a server. And that would store the username and password in plain text in the database. That meant if you got into the database, you would see their username and password. This wasn't very good because when people were hacked, which happened a lot more back then because everything was on HTTP, not HTTPS, happened a lot more. People would just get their password. People would reuse their passwords probably as much as they do now, which is still terrible. But they would get their passwords, they could log into the app, and they could possibly even log into other apps. Then some cool cryptography was added where we salted and hashed the password when it was received by the server and stored a more cryptographic version of this in the database. What this meant was that if a hacker got in, they didn't get the actual password. Say my password is password123, a terrible password. They would not see that. They'd see some random information and couldn't get back to the original. At least this meant that if the hacker got in, they couldn't compromise other accounts of yours. They could just compromise your account with that application. Then we started seeing a lot of adoption of email and password systems. And I think the big advantage here was recoverability. People started to realize that an email system is also a communication system, right? And that you can recover somebody's password by sending them a verification link or a verification code to their email, which allows them to recover their account if they forget their password. Very handy. But this also got us into a problem, which is that it started relying on the email provider, which is a very centralized system. At least with username and password, everyone still controlled that. With email, you would then delegate your control to whoever was providing the email to you, whether that was Hotmail or Gmail or wherever. So it added a lot of centralization to the system, but it added some really important usability features that were needed to make this work. And then we started moving on to the single sign-on paradigm. This is things like the Google login button or login with Twitter. Basically, you can log into lots of different applications with one account. That's called a single sign-on system. And yeah, there's several protocols that govern how to do this. It started with OAuth, we moved to OAuth 2.0, and now the latest in this is OpenID Connect. But they still follow the same paradigm of having username and password and then storing a username and salted and hashed password in a database. This is now stored in Google's database if you're using Google login for everything, right? It has some advantages and disadvantages. It increases centralization a lot more to whoever's providing these SSO services. But as long as you're trusting that provider, they may provide better security than each of the individual email providers that you may be using. So people do generally trust that the security behind Google or something is pretty good. It is not good enough forever. That's not a property of any security system, but it's pretty good and it's better than users can do. Are there any questions about this slide before I move on? Nope. So we've seen problems with this. Basically, we're seeing that these databases do get hacked all around the world, even from the big companies. And this is a problem because it compromises our authorization to whatever the system is. That's a big problem. And a big part of that is that all of that data is in one place. So a summary of what's wrong with this current paradigm of single sign-on or any of the previous editions. So firstly is an availability problem. There's no way to do a long-term or even short-term guaranteed access to your digital identity, your digital twin. It means in the most severe case, you may have an identity and another day you don't. The person providing you with that identity, because they get to decide, it's their data, they decide you don't have it anymore. This, in extreme cases, happens with sovereign states who decide to deny people access to their identity, or maybe a system goes bankrupt and you can no longer access your data or something like this. It gives you no right to privacy. Your data is stored and controlled by somebody who you're choosing to store it with. Somebody else is managing it. That means by default, your data is not private. Somebody else has it. And that leads to the next problem, which is they have the data and you don't have any transparency over what happens to that data. You can't consent implicitly on what happens to it. So they may process the data. You can't really see how they do that and who they sell it to, and who they share it with. They may give you screens, but you can't implicitly prove who you're sharing the data to. And this is a point we all know about. There are big data mining models out there where people sell your data onto other parties as a business model, and there's no transparency or consent over this. It leads to massive single points of failure. If everybody's identity data is in one database or one data system, if that data system fails, either maliciously or accidentally, that causes huge problems. So we all know that decentralized systems are far more resilient and far less likely to fail. A related issue is because everything is in one place, this creates a really high value honeypot for hackers. So that means it's much more likely that hackers actually want to get to this database. And because of these issues of the single points of failure and high value honeypots, this is a reason why we're starting to see a lot of data regulation coming out, really trying to target this issue. GDPR is and was the leading regulation and still is, but there's now a lot of state nations starting to replicate GDPR and its consequences all over the world, trying to deal with this issue here, people's identity data being misused. Again, all of this data is in one data system, and that creates silos. It basically means the data is there in maybe Google's database or maybe your state nation's database. If you want to move that data somewhere else, or if somebody else wants to get access to that data on behalf of you, it's really hard. You have to go through their server. Every server has a different interface for how to access data, a different authorization protocol. So it's really hard to move data around. And this is a big issue for all kinds of data systems out there. Really makes it hard. And also for the user. The user may want to switch their identity and use it on different places. That can be really hard. I can't switch my Google identity and say, I want my Google identity to now be used through this provider. Not possible. Lastly, and as importantly for the user, it's severely degrading user experience to have to reuse your identity information on all of these different websites. Single sign-on did help this a lot, but you guys have been on the internet. You know how often you have to repeat your first and last name, not to repeat everything else, on all of these stupid forms all over the internet and create accounts and passwords. It's so annoying, and it could be better. And just the amount of passwords, the amount of information we need to give out time and time again is just horrible. I have a question here. Do you have any ideas how to store a lot of data more efficiently in the new method? We're going to get to the new method in a moment, okay? So I think if you haven't watched this video here, this gives a brief introduction of public-private keys and how that works. It's an integral part of self-sovereign identity and the upgrade we're about to talk about. And please check out this link. So this is the basic premise of self-sovereign identity, okay? Right now, this is just drawing out. I have a question here from Mikhail.
Yes, Jack, we can't click the link on your presentation, I guess.
You can when I share it with you.
All right. Yeah.
Right. So continuing here. So this is a comparison of basically the old model, username and password, and the new model with self-sovereign identity. So in the old model, as we saw, the username and password is basically stored in the database. Sometimes some cryptography is added, but basically, if the database is compromised, your identity and authorization is compromised. With self-sovereign identity, the first big step that was added was to use asymmetric encryption, asymmetric signing using two different keys. What this does is it puts the private key in your device and only puts a cryptographic version of that on the server, okay? What this does is it means that your secret, your private key, is not revealed on the server. If somebody hacks the server, they don't get access to your private key. That private key can be generated in a number of different ways. It can be done from a mnemonic. You could create the private key randomly. People can create it themselves, or you can even generate it from a password in secure ways. But basically, you get a private key that corresponds to a public key. There's a special property with this, is that I can create a digital signature with the private key, and somebody can verify it with the public key without the private key. So what that means is I can verify that you are you without knowing the secret that you have. So this public key is put somewhere publicly, and that place is called a decentralized data registry. And this is kind of like a combination of the server and database. It has the logic and the data storage capacity, but it additionally has the capacity to be decentralized. So it doesn't have to be. A lot of this tech started with blockchain, so having decentralized stores. And basically what these blockchains would do is they would store your public key on the blockchain, right? So that means anybody that had a piece of data that was signed by a private key can look at the blockchain, can verify that you must have signed the data without you having to reveal your private key, which never leaves your device. So this means that if somebody hacks the blockchain, let's say, all they can see is random information, like basically random bytes. It doesn't give them anything. They can't go and steal your information. And this is particularly important because a lot of blockchains are in fact public. All of the public information, I can even go and see it. You don't even need to hack them. That's how secure this is. You can have this public information out there in the world. Now, I should note, again, these decentralized data registers, a lot of them are blockchains, but it doesn't have to be a blockchain. It can even still be a server and a database. That is possible. It's kind of an agnostic view on how you store it. But what's important is that it can be decentralized and that it uses public-private key technology, which is way more secure. So that's the first step, okay, of the SSI journey. What this already does, just that switch, is that it means, depending on the data registry, if it's a public blockchain, so like Ethereum or Bitcoin, if it's one of these, you get a guarantee that it's an always available identity. You know that Bitcoin is not getting shut down, or Ethereum, and then you can always go and access those public keys, and you can always access your account on that network. The history of that account is always even in music, so you can always prove you have your identity. So it's always available account. The second is by having a decentralized data registry, and again, not all of them are decentralized, but now you can make them decentralized. You remove the single point of failure, and you remove the high-value honeypots. Okay, so that makes it much more resilient. And for companies, removing these single points of failure can significantly reduce compliance times and cost. That's the same with the honeypots. Chris, you have a question?
Yes. So you say that the identity will always be available, but we are designing software that obviously creates this identity. What if we go away? We're bankrupt, or we decide to stop?
So this is why I said this is really dependent on the data registry used. If you're using a data registry controlled by a centralized entity, and that entity goes bankrupt, then yes, you can still lose that identity. If it's on a blockchain, and as long as one node in that blockchain is still running, that identity is still available. So that's a special property that applies to specific data registries. And if you're really worried, for example, if you're worried Ethereum might shut down, you can just go sync the Ethereum blockchain, run it yourself, and you'll forever be able to prove that you had that identity because it's open source and an open network. So the next step starts getting... Sorry?
Thank you for answering my question.
You're welcome. So the next step is a bit more complicated, okay? I'm going to introduce what is a DID and a DID document. So these are two W3C standards. I've got the links up here. You can check them later. Basically, a DID is the replacement of your username or your email address. It is an identifier, and it points to your account and on which decentralized data registry, right? So for example, it could be an account on an Antelope network, or it could be an Ethereum account like this, or it could even be, you can see this, a domain name on the existing internet, right? So it points to the decentralized data registry where you're going to find this account's information and the account name. And there's all different formats for this. And in fact, there are all different types of DIDs already. So these are called different DID methods. So Antelope is one DID method. Ether is a different DID method. Web is a different DID method. And they all allow you to find the decentralized identity document, the DID document. And that's this. The DID document is a standardized way of presenting the cryptographic material needed to verify your account. So it's kind of like, this is the information needed to verify a digital signature of you. And the DID string, right, this piece, this tells you how to find this information, which lives on a blockchain or another DDR. And what's special is this DID document, this standard decentralized identities, presents for every single different type of DID, it presents it in the same format. So my Bitcoin account presents it in the same way. My Ethereum account, my existing web identity, they all get presented in the same data format. And that's going to be really important for a very special property later. But basically, it's the way to see the public keys that correspond to the private keys of the account. In many cases, it's just one public key. In some cases, it's multiple public keys. So how this fits together. Oh, sorry. I'm going to go to this one. If you look over here on the right, basically, you have some private keys in your device, and they create and control a DID, right? They create a DID string, an account on a decentralized data registry. And on that registry, you store the DID document, which is the public keys. Is this making sense for everyone? This DID document is a special standardized format for displaying these public keys. So let me.
Can you go back a little bit? No, you walk through it. So on the right side is the new version, and the old side, on the left side is the old version, right?
This is the self-sovereign identity tech stack.
Right. So it starts at the. Let's walk through it.
So this is all in the client application.
Right.
I'm going to talk about credentials in a second. So this could be a mobile app. It could be a server. It could be a key card with a chip in it.
Right.
They have private keys in it.
Right.
And corresponding to those private keys, the public keys are put on a decentralized data registry.
Right.
And then this device has a DID string that corresponds, that tells people how to find those public keys. Tells them where to find it, on which DDR, and then tells you which account on the DDR. And with that, you can resolve this DID document, which contains a list of the public keys.
Right. So, and the information, so it's like a giant archiving box, right? And on demand, I ask for, hey, can you see if my archive is there? But it doesn't contain any information besides the fact that indeed that is my folder.
Yeah. So there's two pieces. The DID string, that's this. That's a pointer to the DID document. And the DID document, the information lives on a blockchain.
Right.
On each blockchain, this kind of content, the public key, is stored in different formats on different ways. But there's a special method called document resolving. And by doing that, you basically pull all of the information from each different DDR into the exact same format. So each blockchain and each DID method is now creating this special function. Every single one of them has it now that wants to be a part of SSI. They're creating this function called a resolver that allows you to take a string and then turn it into a standardized document. So no matter how your public keys are stored on a blockchain or on another DID method, it will always display them in the exact same W3C standard format. What
Does
this does...
Does this mean that it could also interact with non-blockchain systems?
Absolutely. A DDR can be a non-blockchain system, and there are already. For example, DID Web is a way for self-sovereign entity to stay backwards compatible. So web is actually basically how to interact with the old IP address system and the identity system around that, X509 certificates.
Okay, and if multiple solutions have these this implemented within their system, our system or your system that you're proposing right now, does that mean that even if they are not actually connected to each other, that I could take my document from the one system and put it into another system? It automatically is compatible?
Let me continue, and that answer will be answered. Mikael, you have a question?
Yeah, sure. Can you just give an example how my grandmother can use your technology and how, in the same time, my 5-year-old nephew can use it?
I think that will be answered later on as well. Okay.
Yeah, sure. Okay.
It's really going through how it works, but that will be answered.
Like a benefits for them as well.
Of course, yeah, that's definitely part of this.
All right, thanks.
So I just want to show you how identity data works in the current Web 2 paradigm, right? Your identity data is like your first and last name, right? Or it could be a medical record, or it could be your university certificate. Assuming they're all digital, basically in an existing web app, you basically create that data and you send it to the system, right? And they store that data, again, in plain text in their database somewhere, right? If I want to share my data with somebody else, I have to go and ask them to do that. So to give an example, I've got a medical records example here. Alice, the patient, goes to a hospital. A record is created at the hospital, right? She might be inputting some data, or the physician might create this data. Alice's data gets sent to a hospital server, which puts it into a database. Alice's information is then in a hospital database. Alice wants to use that data later on, right? She wants to apply for some medical insurance, and they ask her for her medical records. Now, Bob, the insurer, has to go and request from the hospital to get that data. So they make a request to the hospital server. The hospital server has to reprocess the data, check it's valid, probably even check Bob's identity in this process. And then to fulfill the request, they send that data back to Bob. So it all goes through this centralized server. That's how internet identity information currently works. So in the new method with self-sovereign identity, basically what happens is these credentials get stored with the user or with the device, with your identity. And we use the DID document to be able to prove that to other parties without needing to go through a third-party verification service. So the way that works in our little example, okay? Alice, the patient, creates her account, and in that process creates the DID document and the public keys. Those public keys get stored on the decentralized data registry. Okay, then she creates this medical record, whatever it is, and she signs that medical record with her private key, which only she has. Now what she can do is she can send that record directly to Bob, the insurer. So Bob then goes to the blockchain, retrieves the DID document, and then can verify that Alice must have created this data. At no point does this record actually go to any system. It gets in this flow here, and this is a simplified flow. It's stored on Alice's maybe phone, and then it gets sent to Bob, who's using a computer. and Bob can know that Alice has an identity and how to verify the information on it. Of course, in many flows like this, you might have a doctor that creates Alice's medical record and then shares it to Alice. So this is a simplified flow, but the same principle applies. Alice has the data, and then somebody else can verify it later without having to go through any third-party service. So I've got some questions. Mikhail. Oh yeah, so we lost the doctor. Yes, a doctor is typically involved here. A doctor might be the one that creates the record. And in this case, they'd send the record to Alice's phone. Alice would verify that the record was indeed created by the doctor. The doctor has an identity and then accept it. Then Alice can send the record to Bob. Bob can verify that it was sent from Alice and that it was created by the doctor. All of this not going through a third-party service again. Does that answer your question, Mikhail?
Yes, sure.
Rebel, what if Bob shares Alice's data? Yeah, that's right. So Bob could then share Alice's data, and Alice wouldn't be able to see it. You can technically do that. It doesn't prevent that from happening. But at least in this system, because when Alice has the data in her phone, she's at least definitely controlling when that is being sent to somebody else, because the only way that's happening is you have to actually send it from your phone to somebody else. If they have the data, you don't have technical control of what they can do with it. There are some legal, let's say, properties of these records called a verifiable credential that are being added to deal with this situation. They're called terms of use. It's a property in a verifiable credential that specifies how you're allowed to reuse the data and stuff like this. But at technical level, it's not enforceable that Bob can't share it to somebody else. Any other questions?
I think there is a technology which can prevent it from copying, right? So even to make a photocopy, so we can like somehow solve it, right? So people like a Bob, he won't be able to make a photocopy of the screen, right? So it will be shaded somehow, right? And on top of that, it can be shared as a picture only, so they can visually check it, and that's it. So otherwise, they will need to make a screen, right, and then try to convert it to the text.
Yeah. So here, what I'm talking about is the data flows, not necessarily what's on the screen. The screen can display all of this VC or part of it. And yes, you can screenshot a phone, but this device here, Alice, it could be a computer. This could also just be two businesses sending VCs to each other. So at a data level, there is no way of stopping Bob from copying it, I would say, with this architecture. I don't know of a good way of stopping people from copying data. One of the inherent properties of digital data is it's almost free to copy digital data. That's why the internet is so powerful, one of the reasons. So I would hesitate to say that we can solve this problem of forcing or guaranteeing that Bob can't copy it. I don't know of a way anyway. Rebel, if a lot of parties ask for Alice's data, won't Alice be spammed with a lot of requests, or will this happen automatically without asking Alice? This is not a question about how SSI works, but how you implement this system. So SSI doesn't really get into this problem you're talking about, Rebel, which is what happens if Alice gets spammed with requests for this record. That's not part of the self-sovereign identity standards, but it is a valid concern and should be dealt with whatever system is implemented. Yes, there's a question about forgetting the private keys. I'm going to talk about that in a second. I'm going to move on. Hopefully it becomes clearer as we go through. So what's important to see here is that this standardized document, this DID document, allows anybody to go and verify this data. And this the public keys corresponding to Alice that are needed to verify the data can be on any different type of decentralized data registry. And this VC can then be verified on any decentralized data registry. That makes it extremely portable. So this data can be created on a Bitcoin network. So suppose the doctor is using their Bitcoin identity, Alice might be using Ethereum, and Bob might be using a different one. They all get to decide which identity system they want to use to sign and use their data. And this data here up at the VC, because everything has been standardized at the layer below it, all public keys are in a standard format. Everybody can always verify this VC and where it came from, even though it may be on different identity systems. So at the VC level, your identity is pretty agnostic to where it exists. That's a really important property. And I'm going to talk about like basically the impact of this next step. So now we're starting to talk not just about the authorization secrets, your private key and public key. We're now talking about having credential data, your actual usable, practical information that you use in the world. And now this information can live exclusively in your phone, and you can send it directly to other people. What this means is that you get privacy by architecture. Because you control the data, you control who you send it to. Nobody else necessarily needs to see it. And there's an asterisk here. It depends, again, on the identity system. You may still have that medical record, might still be stored in the hospital. Depends on the system and how they implement it. There are reasons for having a medical record stored by the hospital still. But in SSI, it's agnostic to whether that does or doesn't happen. And in SSI, you can now have much higher privacy. You can even have privacy where nobody else stores your credentials, only you. And because of this, you always know who you're sending your credentials to, because you're the one who has the data, and sending it to the other person requires you to send it to them. Like we saw before, it's removing the single points of failure in high value honeypots, both by decentralizing the public keys and also by having the private keys decentralized on every single user's device, right? If I want to hack somebody's private keys, I need to go and hack every device now. That means there's really no way for me to get everyone's authorization secrets all at once. It's possible. Now, this is the really exciting and interesting part of the work that's going on in SSI. The way that they've built this DID document standard and the VC standard, both are W3C standards. So that means that your identity, you can use multiple identities on different systems, and each person can still verify your data because they've been put in standard format. The VC format is also standardized, so it means everybody will know how to understand and read different VC documents out there. And lastly, just want to mention, because you can now send them peer-to-peer without a third party, this has some significant scalability benefits. You don't need to depend on a third party, which just takes them out of the equation, reducing friction. The last major one is usability. If you can have an identity in which you can choose and it's reusable across the whole internet, you don't need to type into all of those forms all the time. All you need to do is consent to sending the data. It's a massive usability improvement and a security improvement, because you can possibly have one account for the whole internet, in theory. So just giving you a look at a verifiable credential. So this is the data standard. Again, it's written out here what that standard looks like. The verifiable credential is an agnostic piece of data. It's often presented as a JSON document, much like the DID document. It contains an identifier. So this is an identifier unique to this piece of data. It contains a subject. This is the actual identity data. So this might be the medical record or a university certificate, or it could be a password information. And it contains a proof, which has a digital signature, which is what allows somebody else to verify that it was created by you at a later point in time. So just quickly looking into those pieces themselves. So this is an example of the credential subject. it specifies that this account here, Jack's account on this blockchain or on this DID registry, is an alumni of this university. This is the name of the university. And in fact, this is a multilingual example. It shows how to display that university names in 2 different languages. So this is an example of the actual record itself. And there's some special other information that's included in all VCs that allow you to understand what information is in here, whether it's university credential, whether it's a medical record, whether it's password information. That's also part of this verifiable credential spec. And lastly, the proof. So this is an important piece of information. It just contains a digital signature. That's this one down here. This looks like garbage to everyone, of course. This is in a particular format called a JSON web signature. And inside the proof, it tells whoever's reading this what type of signature it is, where the public keys corresponding to that to the signature are, and then the signature itself. So that's in the verifiable credential spec, and that's what everyone is complying to now. Right, so I think at this point, we could do a small break for 5 minutes and then recontinue, give everyone a bit of time to think about it. Maybe at this point, it's a good idea to ask any questions before we leave.
Yeah, so I do have a question on I had a question still on the moving of DIDs in similar systems. So let's say 2 different banks employ this system, or a bank and a doctor employ this system. Can the DIDs theoretically interact with each other or move from one system to the next?
Yeah, so one bank might have one DID method.
Right.
They might have something called DID, I don't know, Revolut. And the other one might be DID ING.
Right.
So you can basically, yeah. So the important thing is the VCs.
Mm-hmm.
The VCs can travel between these 2 systems completely interoperably. I can use my VC created with ING, send it to Revolut Bank, and they'll be able to verify it instantly and know that it came from there. If your question was more like, can I change my ING DID to a Revolut DID? Is that your question?
No, but I would imagine that would not be possible, right?
You can't like change one DID to another, but you can link them together. There's a feature of DIDs that says this DID is actually now equivalent to that DID. You can do things like this, and there's all kinds of cryptography to do this. But one DID is not necessarily another DID, and you can't necessarily move one DID to another. So the idea was creating this abstraction layer at the DID level, to abstract away all the differences and all of these different DDRs, so that at the VC level, everything's fully interoperable. But at the DID level, it's not necessarily interoperable.
So and the VCs are the credentials itself. So basically the way that I log in.
No, so there's like the login part, which is your authorization, proving who you are.
Yeah.
That's the public-private key relationship.
Right, that's not the verifiable credentials.
No, that's my private key. I prove I am. And you get like your username, which is your DID string.
Right.
Anybody can use that string to find your DID document, which gives them the public keys needed to verify the private key signatures. What you can use that for is a VC. So the main application of DIDs is VCs at the moment. I'm going to show you a few other ones, but the main applications of DID is to use VCs in an interoperable way. So I can then sign a VC with my private key, and that is a form of authorization in a way. And then somebody else can use my DID document now to verify the VC that I created.
No, I'm really sorry, but I still don't get VCs apparently yet. So the VC in what you just said is the VC is a combination of the DID and the private key, and I can use that to verify that that's correct.
They're all related. I
Yes.
created a private key.
Yes.
I create an account on a decentralized data registry.
Yes.
That implicitly creates a DID document. Okay.
Right.
The DID document shows the public key information that's on the blockchain. Let's go.
Right. Do I have to create a DID?
Yes.
Okay.
You have to create a DID.
Yeah.
Your public keys should go on a blockchain or other DDR. So your public keys are here. Now each blockchain or each DDR stores them in different ways, right?
DDR.
Decentralized data registry.
That's the bottom one. Yes. I see.
Yes, where we're storing it. This could be a blockchain or something else. So I have some public keys that correspond to the private keys. I store them on a DDR. Each DDR stores them in different formats, but by having a resolver for each DDR, it resolves those public keys into the same standardized format, the DID document.
And the resolver, that's the VC?
No, the resolver is the way to turn the public key on your DDR into the standard format that is standardized across all DDRs.
And this is just a thing that happens when you enter the DRD.
Yeah, this is if I have somebody's DID,
right,
I use the resolver to get their DID document.
Right, and the resolver is a universally accepted format.
Yes, exactly, because it's a W3C standard. So now the DID document I have is a standardized format for me to understand public keys. What I can then use that with is the VCs. VCs are the best use case for DID and DID documents at the moment. And what it means is that the person with the private key can sign a credential, maybe it's a medical record, and then whoever wants to can see who signed it and now receive the DID, resolve the DID document, and basically prove that it was signed by who sent it to you.
I can see it and use it to verify that it came from you. Use it to verify you.
Use it to verify the data and who created it and who sent it to you. So this is like the practical real world data. So this is the real world kind of use case. I know it's still an abstract data format, but this is the real world data, the credential, something that's happening.
Mm-hmm.
Private and public keys are just random bits and bytes, right, that we create. But now we can use them in a special way that I can prove I created this credential. Somebody else can verify that without having to know which DDR I'm using even, because there's a standard interoperable way of resolving and understanding the public keys.
So that means that I can attach your system to my business system, and my users don't even know that they're interacting with this system.
You could do that, yes. I could create a medical record on my phone from my, I don't know, Facebook identity, if Facebook had a DID method, which they don't. I could create a medical record on Facebook and then send it to my friend who doesn't know anything about Facebook. And this technology allows him or her to verify this medical record I created on Facebook.
Does this mean as well that these documentations and, for example, these DIDs could be temporary outside of the blockchain system and then re-enter the blockchain system again?
Maybe. Not sure. I'd have to think about that.
Because you're saying that DDR is on the blockchain or something else, and it's a universally acclaimed standard.
Yes. So the standard is the DID document.
Right.
Where it is stored is agnostic. It could be a blockchain.
Right.
It could be a web server.
Right.
There are even like more crazy DDRs that I won't mention here. But it doesn't say where the data has to be stored. It just
Exactly.
says that it has to resolve to a DID document.
So as long as my system does this small part of translation,
Yes.
it doesn't need to use your blockchain even for a while. So I could take your data that I'm getting from your system, use it internally in my company, doing whatever I want, and then return it again to your system onwards to the next customer. Would that be
Would
possible?
be, yes. So I create some data, I sign it with my DID, gets to a company, they sign it with their DID, they're using a different DDR, they then send it to another company or back to you, and everyone can verify both parties did what they said they did, even though they're both using different identity systems, different DDRs.
So different companies could have different levels of transparency if they wanted to.
Indeed, like this could be a public blockchain, it could be a private blockchain, it could not be a blockchain, it can be all kinds of other things.
Very interesting. So I can use the blockchain advantages, but I don't need to suffer the disadvantages. Interesting.
It's a choice, and this is what I said. There's, let me show you here. This DID string is specific. It tells you which DDR, and each one has to register a type. And there's a growing list of how many different data systems support the DID protocol. So you could create a Facebook DID method, for example. Facebook is an identity provider. It is theoretically possible to make it then interoperable with this standard. Google could do it as well, whatever. And you can create new ones.
So theoretically, I could actually save my data. I can leave, if I have a Facebook account, I could potentially leave Facebook, but still get all the information of Facebook into a new system if they actually give it to me.
Yes, but you still need them to make constantly available.
Yes, in this format.
Your public keys, and if they shut down their servers, and because they're centralized, they can choose who to share it with. Yeah, you're at their whim still. But in theory, that could happen.
All right. Thank you for answering my question. Do we have other questions, guys?
Cool. Let's take a 5-minute break. We will meet at sharp. We will start sharp in 5 minutes. So 2 minutes past past. Okay. See you guys then. Okay, we are starting again in 1 minute. So get ready. I will wait till it turns 3 past, and then I will begin. There we go. Okay, so I do want to quickly mention that verifiable credentials are just one use case for the DID document. And there are a few other things I want to mention here, but there's also a lot of other different types of self-sovereign identity components being built right now. The first, I think this is the most important one, is something called DIDCOM. Basically, this is a way to do peer-to-peer communication. If there's a way to get everyone's identity information, their public keys in a standard format, you can then use that very easily to send messages between each other, no matter what identity system they have. That's DIDCOM. The second is a sub-feature of VCs, which is basically a way using some zero-knowledge proof and other types of cryptography to share part of your credential without revealing the rest. So, for example, I could reveal from my date of birth credential, I could reveal that I'm over 18 without revealing my actual date of birth. Things like this. We won't go too deep in these. I just want to let you know that SSI is not just DID and VC. There's actually a lot more things going on. I think these are two very important parts. There's also others. So there are definitely some challenges for SSI. I want to go through these. These are very important. The first is usability and recovery. So somebody's already asked a question, what if you lose your private keys? Now that's, of course, a big usability problem in public-private key technology, because if you lose the private key, you can't get it back. And if there's no way to recover it, you've just lost your account, maybe forever. So this is a big challenge that people are trying to work on. In the Web 2 systems, this was solved by somebody being a full custodian of your identity. Then it's simple. They are able to recover your account for you. But with public-private key technology, that's not necessarily possible. And just generally, there's a lot of cryptography involved. There's blockchains, even more things. And giving this in a way that doesn't present this with a terrible user experience seems to be very hard. And a lot of different solutions are out there. And creating the right usability solution that feels like a Web 2 application, that doesn't present you with cryptographic material. You don't even need to know what DDR you're on. You don't even need to see your DID string, I would say. This is a challenge that the whole self-sovereign identity ecosystem is going through. This is a shared problem that a lot of the blockchain industry is also going through, the same kinds of problems. So related to that, with owning your private key and owning your data, you're also sovereignly owning that. You're also then responsible for controlling that data. And can we build resilient enough ways for users, resilient enough software that can allow users to be responsible enough for that data? Is that going to be possible is a question. Or do we always need to have central agencies in control of your data just because users are not responsible enough in general. So this is an ongoing discussion and challenge in self-sovereign identity. The next is interoperability. So this is an interesting one to bring up because interoperability is, of course, one of the main advantages of SSI. So the DID document, as I've explained, gives this abstraction layer on top of the DDR. Everything on top of that is then interoperable. But of course, each DDR itself is, in a way, itself its own unique system, its own unique identity system. And those parts there are not interoperable. Ethereum is not interoperable with Facebook. And Facebook is not interoperable with Bitcoin. So you still have some non-interoperability. Some people have trust issues with one thing and not others. I may feel like my Bitcoin account will last forever, but my Facebook account might not. So there is differences in these DDRs, of course. And the last is just the recognition and adoption. So this is very high bleeding edge tech, and getting a lot of developers to understand this and start working with it is an ongoing part of what's happening. I just wanted to mention these four. These come to the surface for me in my experiences. There's, I'm sure, other challenges that are important. Yes, there's an important question here. This is related to usability. So anyone that wants to use a Bitcoin identity, that wants to update their identity, for example, is going to have a usability problem because that literally takes 10 minutes to an hour. That is a usability problem related to the specific use of certain DDRs. There are blockchains that just have terrible usability features from their particular data model, and some don't. So who's involved, right? These are W3C standards. What does that mean? W3C is the World Wide Web Consortium, and they are the group in charge of the standards of the internet. They are the ones who decide on HTTP and SSL certificates, X509 certificates, how all of this works. This is done through the World Wide Web Consortiums. It is a consortium of members that I'm pretty sure you buy into. The main four are Google, Amazon, Apple, and Mozilla, who are the main four web browser providers. So they're probably the most important stakeholders here in how the internet works, because we access the internet through our web browser almost all the time. So they're governing these internet standards. The DID document and the VC is a W3C standard, and they're governed through the working groups within the World Wide Web Consortium. There's a DID working group, there's a VC working group. There are also other subgroups like the W3C CCG, the Credentials Community Group. This is different from the W3C DID or VC, and you don't have to buy in as a member to be part of them. The Credentials Community Group, for example, is an open access working group of the W3C. And it's how I've done some of my work in the past. So both of these are a proposal to create a new internet standard, so a new HTTP, for example. And right now, they have both gone through the process of being a draft and to being the next level. Now they're at a recommendation. Recommendation is the last level. What is a recommendation? It really means that this is now a new internet standard, recognized and accepted by the World Wide Web Consortium Group. It's gone through their voting process of several years to get to this stage, and it's shown enough adoption that they have now accepted it and are recommending to people to implement these as internet identity standards. So I don't know if this will happen, but I think based on this, we could start seeing browsers, instead of typing HTTPS and then your web address, you can possibly put in DID Ether, and then you can resolve a DID through your browser. It's as easy as that. That is one thing that maybe could happen from this recommendation status. So it's big stuff because it's gone through all of this process already. There's a huge community around it. So you've got the W3C. There's a lot of people working in that already. all the major browser providers. Another really important member is the Decentralized Identity Foundation. It's a specific membership organization, just like the W3C, that's just specifically looking at DIDs and VCs and the applications of those. So it's like a really focused W3C. They're, of course, all working together. Then you've got a bunch of big groups like the Hyperledger Foundation, the Ethereum community, including the Ethereum Enterprise Alliance, Sovereign Foundation. Some state nations aren't directly, but are indirectly through several of their funding programs, investing a lot of money into self-sovereign identity. IBM and both Microsoft are both on the bandwagon. There's the rebooting Web of Trust, which is happening right now in the Netherlands, actually. And then there's all kinds of other members. There are each individual blockchain that's creating the DID resolver, a very important piece. All the people implementing VCs for wallets and more. So there's a lot of different people involved. These probably the bigger ones. So why is this system so important? So first, I do want to refer you back to that Christopher Allen video that I shared with you. It really goes into this in a lot more detail. I'm just going to gloss over it here. So first, it really gives a system back to its users. It gives self-sovereign control. It increases retention and participation of those users through increased trust. It means that people have possibly less accounts. There's less passwords, there's less forms for people. People are less annoyed. I can see this significantly reducing data regulation work, breach frequencies, and impact of breaches in all kinds of data systems. And similarly, it reduces frictions around verifying data because you don't need as many parties involved. You don't need custodians to constantly verify data. You can send it directly to somebody else. They can verify it instantly. This is a change to the internet architecture. It allows people to have the data on their phone and then for them to send it to their friend or work and for them to verify it. So it really changes the architecture of the internet. It makes it more sovereign, more decentralized, and more resilient. And of course, it has all of these amazing security, privacy, interoperability, and scalability features, which is important from the individual to the company to the ecosystem level. As an example, I want to show you what SSI might mean for democratic or governance systems, right? So your account, your DID, is an anonymized string that tells people how to verify signatures from you. You can use this in voting systems. So you can vote anonymously, but prove that you voted through a VC, okay? And then you can prove that it was counted by putting a transaction in an automatic counting blockchain system, for example. You get autonomous access. If your identity is on some kind of public immutable blockchain, you can get a very strong guarantee that your account will be around forever. And you can prove that you're part of a democratic system. And lastly, because that VC, your identity information, maybe your nationality, your age, your skin color, none of that actually has to be seen and verified by voting systems anymore. You can hold that data yourself, but that's not important for voting. And importantly, it's no longer a technical requirement to verify who you are when you vote, only that you are allowed to vote. And that's a really important distinction for non-discriminatory governance voting systems. Mikhail, you have a question?
No, I just want to give an example about, for example, when you will look for a job, it can be, your identity can be hidden, your race, so you won't be discriminated, your age as well, right? So this is kind of an example of SSI for democracy as well. So during your job research and looking for the job and applying, when you apply for the job, so your race can be hidden, for example, right? So you won't be discriminated.
Yeah. This applies to democratic voting, but also all kinds of other systems, like employment contracts or whatever. Sorry, there is one point here. and the challenges that I did not wanted to talk about. So that is again about interoperability. So I'm going back a bit. But basically, not all DDRs are made the same. Okay. So if you and not all self-sovereign identity systems are basically doing it in the way that I've showed you here in these flows. In these flows, these are showing you the kind of human-centric way of viewing this. It assumes that your credential is in your phone, that you're in control, but that doesn't necessarily have to be the case. You can build SSI systems where the user is not in control, okay? But SSI systems definitely allow this to be in control now. So it's not necessarily the case with SSI that it is a self-sovereign identity system. Self-sovereign identity, the standards allow self-sovereign identity, but even if you use it, you don't have to make it a fully self-sovereign entity that the user has control on. This is really something to watch out for. If this is important for you or your company or yourself, what SSI system you're using does make a difference as to how self-sovereign it actually is. So I just did want to bring that up, especially if you look at systems like Sovereign or anything based on Hyperledger Aries. These are not necessarily designed as the human-centric, fully self-sovereign systems. They're designed as B2B systems where businesses still control your data, but in a, let's say, better way. Right, so going on. I just want to go through a few different use cases of how you can use VCs specifically. These might be apparent, but maybe not. So the first would be supply chain. So, right, I might be wanting to track banana shipments around the world, and I can now use a VC to prove that I sent the package to the next dealer. And that dealer can basically prove that it got sent to the shop, and the shop can then show the provenance of verifiable credentials to the customer, and the customer can verify that the bananas got to them, even though each of the members of that supply chain might be using different identity systems. Because the VC is interoperable, the end customer can still see where the banana came from and verify that. Similarly, with logistics, you could think maybe baggages in an airport system. How many times does that go through checks from different airports onto the plane and off the plane? A very similar idea applies. You can use VCs to basically track all kinds of different systems. The obviously one, when you think of digital identity, is actually your passport information, using that for immigration, moving around airports. Medical records, I've already given an example of. Doctor gives you your medical record as a VC. You can then send that on to another doctor or maybe an insurance party. You can easily use this. And we also had another example of a university certificate. So like a bachelor's degree, or it could be your license, your driver's license. This can be a credential. Now, when it's issued by the government or the university, I can then show this to my new employer or the police that I do have indeed gone to university, or I do indeed have a driver's license, without them having to go and request it from the university or government each time. You just send it directly to them. They can verify it no matter which identity system you use. Michael's had some good question about contracts and agreements, employment contracts, intellectual property. All of these are great use cases for VCs because you can then verify it super quickly and no matter what identity systems you use, significantly reducing legal frictions. You can use VCs for votings, different ways of doing this, but basically a vote as a VC. You can also get proof of a vote as a VC, so I vote, and then somebody sends me a VC to say, yes, you did vote. Then I can prove forever that I voted. Any kind of private property or real estate, so the deed of my house, or maybe the bicycle I own, could be a great VC use case. It really more applies to private property. If it's going to be public property, you don't necessarily need to have it as a VC. You still can, but you can put it in a public place as well. That may be a better way to do it. So private property and private real estate are great examples here. And the last one is a ticket to an event or a receipt from a payment that I made to buy some bananas, maybe. And then I can prove that I had the ticket or that I bought the bananas in the future. So that was it. I just want to quickly tell you all about the Tonomy Foundation. So we're a non-profit focused R&D foundation. We're focused on ethical open source development. We're building our first project, the Tonomy ID self-sovereign identity suite. We're doing a design-led process with a great team here based all around the world. And certainly we are looking for people to help with us. We're looking for contributors like my glorious team that's joining me on this call, as well as early stage investors or tech adopters that are ready to use this kind of technology in their system. So we're building this Tonomy ID project so that you don't have to handle all the complexities here, and we can allow you to use VCs or DIDCOM in your application really, really easily, and really, really easily for your users as well, not just your developers. So after that little plug, maybe it's time to just ask any final questions about some of the other content.
Before we go into that, let's have a round of applause for Jack. Everybody, can you please unmute your mic and clap for him, please? Woo!
Hey, thank you, Chris.
Great presentation. Thank you very much, man.
There is an automatic noise reduction when you're clapping, so just it automatically reduce sound of clapping.
That's
but
funny.
we have clapped, Jack, many times.
Yeah, thank you.
Questions. I'll head off. I'll head off with one that I had very, very early on. Going all the way back to the problems that you see in that this solves at the very beginning. So you had like a list of 9 or 6 problems.
Oh, yeah.
Coming back to that, which 3 of them do you think are actually the most pressing, or do you think have the most direct business needs to resolve?
So the most pressing for businesses?
Yeah.
Definitely number 4.
I would say 4, 5, and 7. Yeah, so like just the security and privacy problems resulting in compliance costs, either because they have to comply to them and that takes work and time, or because they have a data breach and that then takes work and maybe and then there may be a lot of fines. And the second is usability. It's also related to trust. User retention is related to trust and related to usability. So I'd say basically the user retention and participation related to usability, and these first 3 actually.
Thank you for that. So the user attention, what do you mean? That's not something I see listed here, or am I not?
These are kind of like the direct data problems, and the kind of impact of that is more what I'm talking about. The user onboardability, the user retention after they're onboarded, and how much they participate is affected by these first 3 and the last one. I think that's very important for businesses.
Do you also mean with the attention, like oversight? So the idea what's going on?
I'm saying retention, not attention. Do they stay in your system?
Right.
So onboarding, retention, and participation is all related to the trust and usability of their app. And if that sucks, the trust or the usability, then people will not join or leave. And that's important for businesses. And this solves critical problems in that.
Cool. Thank you for answering that question. More questions before I ask more questions? I'm going to give other people also a chance.
I'm on my behalf.
Go for it.
Oh, no, I didn't have any questions. I just said no, not on my behalf.
Okay, cool.
What about my grandmother and my nephew?
Yes,
Ah.
I was just about to get to that.
Well, I was hoping that this this example would quench your thirst.
Mhm.
Yeah, so for your grandma, her medical record, the VC, when she goes to see the doctor, can now be sent directly to the insurer. Is that a good enough example?
Well,
She won't know that. In my mind, she doesn't know she's using SSI at all. Her
yes.
application doesn't show
Yeah.
her that, but she is, and she's getting the benefits of that.
Okay, so it means no one will steal her data if she worries about that. Same for the nephew, right?
I can't, and nobody can prove, nobody can guarantee nobody can steal your data, because you can always steal somebody's data if you try enough, but it's way harder in this way.
Sure, but for example, with a doctor, you don't need to share your name, right? For
Mhm.
example, and if they steal data, so they need to put your name and like to make a copy out of the screen and then to put your data, I mean your name on it, right? So it will take longer time, right?
Well, I'm more thinking like when you create the appointment, you would
Yeah.
sign into the hospital portal.
Yeah.
The hospital would request your first name credential. You would click a button that would send it to them then,
Mhm.
and then they have that. You don't, and then the data gets sent to them. So
Sure.
this is different from having to fill. Nobody has to fill in a form anymore. You just
Yeah.
send that same credential over and over to people if they want their first name.
All right. Thanks, Jacob.
I have a potential way of filling in this thing, but please correct me if I'm getting it wrong. So imagine that your grandma has gone to the hospital and has seen a doctor and gotten a very heavy diagnosis. With a heavy bill attached to it, right? And the doctor asks for permission to proceed. Maybe your grandma wants to have a second opinion about what's going on with her.
Mhm.
Now, maybe she can take all the information of that doctor that she's already seen now, because she owns it, right? And her medical record, and go and speak to an independent doctor, let them see the information without them ever having to talk to each other. So they get a neutral opinion twice.
Right. Yeah. So great use case in a lot of places around the world. If I want to switch GPs, I have to go and request my old GP to share my data with my new GP. It's a process. There's all these forms. It can sometimes takes weeks. I've done it. It has literally taken weeks before. And now it doesn't even need to be done because you have the data and you just share it directly with them. They can immediately see that it was indeed a doctor that created it. So it's just this instant thing that can now happen.
Even better example, you are in the hospital, right, with your grandmother, and you can send the data to another doctor without leaving literally the hospital, right? So you just send the data. Doctor sees like online, and you can create even this application for the remote medical, or how do you call it now? How do you call it? Telemedicine. It's called now telemedicine. So that's how you can use it actually.
Mhm.
If you have some doubts with your doctor, right? So everyone makes mistakes, but so at least it can help you immediately, and it can save lives, right? So it can definitely save lives.
I don't want to, absolutely. I don't want to say SSI is a solution for everything. It's definitely not that. It's a solution for a few problems in the digital world and has to be applied correctly. SSI is the standards-based approach to all of this information that creates these properties itself.
Yes. To continue on to that, to maybe go even further, does this mean, for taking again the medical record example with the grandma, that the grandma could potentially even go to an artificial intelligence and give the artificial intelligence all the data, and then ask it for its opinion, and then still keep the data with herself so that the AI doesn't,
I guess it depends on the terms and conditions of that service. If the service doesn't need the data afterwards, maybe grandma can get it processed, and then the VC, the artificial intelligence, sends a VC back with a report in it, and then she can get proof of what the artificial intelligence does. Now the artificial intelligence program can delete her data. She's got the proof, and she can show that proof to anyone in the future and say, yeah, this artificial intelligence did this.
That's a very,
So
because
these
getting more.
These identities, DIDs, don't have to be for people. They can be for
Anything,
computers, businesses, governments, IoT devices, all kinds of things can have DIDs. I'm really presenting quite a human-centric view of this, but that's not how some people are using DIDs. It's kind of how we're approaching it at Tonomy, and it makes sense by and large for a lot of use cases, but some things, maybe with IoT devices, might not use the DID method we'll use. But the advantage is we'll still be able to use VCs from IoT devices using other DIDs. And I should also make it clear that Tonomy ID is not just an SSI solution. This is just one component of Tonomy ID, the SSI part. There are other features we're building as well, like recovery and signing blockchain transactions and stuff.
Very interesting. More questions, guys.
I'm gonna take one more and then we can call it.
Yes.
I feel like it's gonna be you, Chris.
Yes. Okay. Fine. You spoke briefly about that potentially the IDs could be even simplified to the standard that they are visible in a browser, even without having the having a blockchain app and stuff like that. You could verify or at least see a little bit of the data in the browser. Do you really imagine that it could work that way?
I'm not sure. Like putting a DID into a URL bar would, I mean, the only thing a browser could know to do with that is to resolve the DID document.
Yeah.
Which is this.
Yeah.
I mean, maybe it's useful for developers. So
I would imagine, for example, a supply chain. I have there's a crate. I'm just a shipping company. I don't own the crate, right? But I might want to make sure that it's going to the right destination because I'm paid to do so. So maybe I want to see what's in the specific not what is in the crate, but at least some of the information, so I know it's where it belongs without interacting with the system itself. So I could verify the contents of it or that it's correct without even having an interaction with the system. Is that how that potentially could work?
I'd say yes. Yes, I'm not exactly sure how it's going to be integrated in browsers. I mean, browsers have an identity system right now. So this here is going through HTTPS using SSL certificate, which is a private key, okay? You can see your certificate there with your public private key using the existing certificate system. So this is your current web identity system as it's used. This is not your user identity, right? So for beautiful.a, I've got a user level identity, but internet level identity is using these other ones. SSI is designed to basically, it could merge the two together. It might not, it might stay separate. I'm not exactly sure, it's pretty early days. I think what's clear is that browsers want to keep this technical stuff away from users because I mean, this is like a high-tech workshop we're doing right now, but this is not suitable for your average Bob or Alice on the street, okay? I don't know how browsers are going to do this, but in theory, now browsers are being recommended to adopt the standard. If you look at Brave browser, which is like a Web3 browser, they have the ability to sign in with different blockchain accounts. You sign in with your private key, and then you can sign transactions. They could then use this standard to allow you to sign VCs in the same way, using those accounts you're using in the browser. So it could be a feature of the browser to allow web apps to request a VC to be signed, and it gets signed inside the browser.
Well, I wasn't hoping. That's amazing. If that's what that was not what what I was hoping for. But that's even more than I was actually requesting. I was referring to that you could view the DID in the web browser without being the owner to it or being attached to the network of it.
I mean, if the DID is living on a public blockchain, you should always be able to get the DID for it, right? Because you can always find that public key information. If you're not connected to the network, probably not. There are a few exceptions. Some DIDs work differently, but that's the edge case, not the norm. Okay.
Thank you for your time, and thank you for answering all my questions, and thank you everybody for showing up.
Yep. Thanks everyone, and have a great day. Bye.
Thank you.
For
Have a
hosting,
great day.
Jack.
Have a great day.
Bye.
Have a
Jack,
great day.
thank you. Bye.
Bye.